Let's continue then. Okay, so I'm going to continue with chapter 3. And let me remind you, this is the second lecture on chapter 3. So the second lecture on chapter 3, nonlinear integer programming using Graver bases. So let me remind you the setup. We want to solve, let's say, minimize linear or nonlinear functions over a set of integer points satisfying a system of linear inequalities which come in standard form without loss of generality, so equations and lower and upper bounds on the variables. The dimension is variable, so n, let me emphasize this again, in my lectures the dimension n is variable, whereas in Matthias's lectures the dimension is fixed, so that's a big difference in the method. And we defined a very important object, which we defined last time, was the Graver basis of the matrix. So this was a finite set of integer points in n dimensions and the Graver basis. Basis of the matrix A. Okay, so you remember the definition. Finite set of vectors in the kernel of the matrix. So maybe I should actually say this, the Graver basis of A. Let me also remind you, so this is contained in the lattice of A, which is a set of all x in Zn, x0, x non-zero. It's a finite set. And our goal is now to show that using the Graver basis, we can solve such problems in polynomial time for suitable functions. So the goal for today, well, I'll actually say more, but the main goal is show that we can solve this problem and more, this problem here, in polynomial time if we are given the Graver basis. Okay, this is the goal, and so we are going to do this in a setup where the function is more than linear. So f is going to be separable convex. And this means separable convex function. This means that f of x is the sum of univariate function on each variable separately. And each fi is a convex function. So each fi is a convex function from R to R, so it looks like this. If the graph is something like this, that's a convex function. And we have one separate function for every variable. So these are called separable convex functions. Okay, in particular, note that linear functions are separable convex. Because Wx, a linear function, is the sum of univariate linear functions. Okay, so, and again, linear minimization of integer program with linear objective function is very general and very hard usually, and most literature really deals with this situation. So this is a stronger result. So I'm going to give a sequence of lemmas. I'm not going to prove all of them. You can find them in my book. And So we need some lemmas, so a sequence of lemmas to get this result. So the first lemma is a very simple lemma on univariate convex functions. So first of all, I want to start with univariate functions. So here is lemma 1. Lemma 1. Let f be a univariate convex function, and x and, let's say, x and y1, ym in R. And let me actually say, do we have any eraser here? This one. Let me say that x is in R, and y1 to ym are in R plus. Okay, so I have one real number and m non-negative real numbers. Then we have the following condition. Then we have the following. Then the following condition, which we call supermodularity. Supermodularity condition holds. And the condition says the following. If you look on the improvement in the function where you add all the y's together, this is at least as big as looking on the improvements for each one separately. So this is the first, this is supermodularity of the function. Yes, and I mean, you can see this from the picture somehow. If this is your x, and these are the y's, y1, y2 or something, you see from the convexity that the function goes up faster as you go farther away. So if you add all of them together, it's better than adding one by one. And I'm not going to prove it. This follows directly from the convexity, the definition of the convexity of the function. So it's easy to see. So we are going to use this. The next lemma on univariate functions still is an algorithmic lemma. So let me just try this one. So here's another lemma, lemma 2, let's call it lemma 2. This is algorithmic. And it says again, suppose, let's say S is a set of integer numbers in Z univariate, which lie between two other numbers. So R and S are, let's say R is less than S to make it interesting. And these are integer. And let F be convex again. Convex. Then, in polynomial time, in the natural size here, in time which is polynomial in the log of these numbers, the log of R plus log of S, let's say, and I'm not really, the log is, so this is the binary encoding, I denoted this last time. So when I have several objects and I write them like this with commas in between and put these parentheses, this means the binary size, the encoding of the binary size. I write them as in digits, decimal, or binary expansion, count the number of bits. This is the size. This is the natural size for this problem. Then in polynomial time, we can solve, and this is an easy problem, but let me say this, solve the minimization, this univariate minimization problem. Minimize f of x over s, even if f is given by comparison oracle. So do you remember from last time what is a comparison oracle? It's one of the weakest sort of oracle that gives you a function representation. You just give it two numbers here, or two vectors, and it tells you which one is better. So that's all we need here. Therefore, also we don't, I mean, there's no input size for the function, because we just compare. So we can do it. And this is very easy now. So what is the, let me just sketch this proof. So let's look on how does this thing look. This is these are univariate functions. So this is the x-axis. And let's say r is here. R is an integer point. S is somewhere here. Another integer point. And the function looks something like, you know, maybe like this or something. That's the function. This is the graph of the function here. Is this okay? And now, look, so we assume that this is sufficiently larger than R. So what we do, we are going to bisect, of course, and take one middle point here, the middle point rounded down, and the next point, which is R plus S over 2, rounded down, plus 1. So I take two adjacent integer points in the middle. And now the idea is very simple. So I take these points and I ask the oracle about these 2 points. And I get answers, right? Or in this picture, what would the answer be? I ask the oracle to compare the values. What would be the answer here in this picture? What?
It looks pretty flat there.
Flat, right. So the same, right? If you say they are equal. So if they are equal, so if they are equal, then I conclude that this is a minimum. Now, why is that? So the algorithm is very simple. I compare them. If the answer is equal, then either of these is the minimum. Let's say this one. If this one is bigger, then I'm saying that the minimum is going to be in this interval. And why is this the case? Because, you see, if there, suppose it tells me this one is bigger. This one is bigger. Then I'm claiming the minimum cannot be here. I mean, maybe it's in the middle and it's not an integer point, but I don't care. I look on integer point. So the minimum cannot be at some integer point here, because then this will contradict convexity. So the minimum must be somewhere here, at an integer point in this interval, this half interval. If I get the opposite answer, you know, similarly, it cannot be here, so it must be here. And if they are the same, again, it cannot be here, because then again it contradicts convexity. So a single query splits the interval into 2, and I can then look on a half interval. So this is called binary search, and this leads to this logarithmic solution for the univariate problem. Okay, now we're going to move to vectors, because we want to do vector optimization, variable dimensions of dimension 1. So, so we need some analogs here. So here are two analogs. Lemma 1, I don't know, let's put a hat here. So vector, lemma 1, vector notation. So the same thing. And it says the following now, again, F is now separable convex. Separable convex. Now, X is some integer vector. And, well, can you guess what's going to be the sum now? From last lecture? Sort of here, I wanted them to have the same sign. So what kind of sums have a conformal sum? So conformal sum, just to remind you, this means in particular that all these vectors in the sum are in the same orthant. Not necessarily non-negative, but they have every sign on every coordinate. I mean, on every coordinate, they agree with the signs. Then again, we have supermodularity. So f of x plus sigma gi minus f of x is at least the sum of f of x plus gi minus f of x. Exactly the same thing. And the proof, well, I'll leave this to you also. It's not so important. Basically, because it's separable, you can you break it down to the sum on each variable. And on each variable, because of the sum is conformal, on each variable, all the corresponding coordinates of the GIs have the same sign. And therefore, this holds. So you can work this out. And then there's this analog of the lemma of the second lemma, again, the vector analog of this one, which tells you that now we want to do some other sort of optimization. And so we want to minimize. So, well, consider the problem of finding the best step in a given direction so let me first write a problem, and then we want to minimize f of x plus lambda g such that lambda is non-negative integer, x plus lambda g is between some given lower and upper bounds. So upon finding a best step in a given direction, where x between L and U are given, and f is convex by comparison oracle again. Let's see that I didn't forget any detail here. And G. We need a direction G given, and we also have this G in Zn. Then we can do it in polynomial time. Then we can solve it again in polynomial time. In the data again, the binary presentation of the lower bound vector, the upper bound vector, the given initial point x, and the direction G. Okay, so let's see. Okay, so you see, the problem here. The data, we have four vectors. The data consists of 4 vectors, a lower bound vector, an upper bound vector, one vector which lies between the lower and upper bound, so sort of feasible solution, but still there's no matrix here. Now, if I compare it to the real problem here, we have a system of equations, but at this point it doesn't come up. And we have a direction where we want to actually improve the function, and we are looking for the best step size. So here's our point x, and we're given some direction g, and we want to know how far we can go and improve the function, decrease the value of the function as much as possible while not exceeding the upper and lower bound. And the claim is you can do it again efficiently, and it's enough again that the function is given by a comparison oracle. And here I don't even need it to be separable convex. Let's see. No, we need it to be separable convex. Yeah, so separable convex. F is separable convex. And again, it's described also in my book and the notes you have on the web, so you can check the details. So how do you do this now? Well, so look, this is fixed. X is fixed, G is fixed. So what kind of function is this? This is a univariate function in lambda, and then we simply apply this. Where is it? This. You see? Well, we take the x, we have the g. First of all, it's easy to find bounds on the lambda. What's the largest lambda that will not exceed u? This gives me the s over there. And then I can also see what's the minimum lambda I can take without violating the lower bound. This gives me R. And then I have a univariate convex problem, and I apply this in polynomial time, so I can do this. Okay, good. So now we come to the main lemma of this chapter, really. So let me state it and try to, let me keep this. So here's the main lemma. Yes? Why do I need it to be separable? Let's see. Actually, yeah, you're right. I probably don't need it to be separable. So, well, yeah, that's true. I don't need it to be separable. Good, yeah. So we don't. Yeah. Yeah, it doesn't matter. Just enough that it's convex. But anyway, I mean, we're going to use it eventually for separable convex functions. So, but it's true. It's not the convex. The univariate function is then convex, and we're fine. Okay, so so here's the key lemma. And the lemma is really the algorithm, and it says the following. So let me make it precise. The statement so let me make it precisely. Make the statement exactly precise. Once there's an algorithm, let me make it formal. That given an integer m by n matrix, its Graver basis for the time being, it's part of the input. Graver basis g of a, which is a set of vectors in n dimensions. Then these lower and upper bound vectors, so some of the entries may be plus or minus infinity, so there are no bounds on these entries. And some feasible, sort of feasible point which satisfies the bounds. And a function, now we need it to be separable convex, and separable convex f, which is, let's say, defined on z, and that's enough, takes on integer values. That's important. So again, if it takes on rational values, we just scale it up, so it's not a big deal. Anyway, it's not going to affect the comparison oracle. Yeah, so actually, presented by comparison oracle. So there is an algorithm given this, solves the problem of minimizing this function over the integer point satisfying this. Now let me write a z here. Actually, you know what, let me call this x0. So this is x0, x0 is here, initial point, and lower and upper bounds, that's it. And so let me explain some things here. In time, which is polynomial, in everything. So this is a little bit technical, but I want to, once write the entire formal statement. And let me, so this is about this is a bit technical. Okay, so let me explain the statement and then we'll try to prove it. Yes.
Do you need x0?
Yeah. So okay. So first of all, have you, written it down, or are you? So the integer program is the same type I started the lecture with, and the function is separable convex. In particular, I'll come to it. In particular, can be linear. Now we begin by assuming that we have a feasible point in the following sense. We have an integer point satisfying the bounds, and we define at this point the right-hand side b by this x0. So this makes it feasible automatically. Later, we are going to, of course, find a feasible point, a real feasible point. So there's going to be another lemma, and then there's going to be a theorem. But for the time being, I define the right-hand side b to be a times the given point x0, and this makes it automatically feasible in this problem. So this is one point. The nature, the size of the problem, so let me explain again. The vectors, LU and the feasible point are given in binary. The Graver basis now is part of the input. And this f hat is the maximum absolute value of the function over the feasible set. So this is something we need, and for linear problems, that's very natural. It's no problem. If we have a linear problem, it's just the largest absolute value of w is good enough. And in general, it's not so hard to bound this, to find a bound on the value of the function. Okay, so it's going to depend on this, but everything you see, it's logarithmic. So the dependence is logarithmic. It's the sum of the logs of all these encodings. So let me prove this and describe the algorithm. The algorithm is actually quite simple. So what is the algorithm? Proof or algorithm? Proof outline and algorithm. Well, we start with the feasible point, and we produce a sequence of points, feasible points. x0 is a given point, x1, x2, and so on, up to some xs, and then we stop. Feasible point as follows. So suppose we already found xk, then we let xk plus 1 be the present point plus lambda actually, let me write it. Let x plus 1 be the optimal point of this. Now, minimizing f of xk plus lambda g such that xk plus lambda g satisfies the bounds. G is in the Graver basis, and lambda is non-negative integer. Yes. So let's see. First of all, let me see if the algorithm is clear, and then we'll justify it. So what does the algorithm tell you? You start with the feasible point. At each point, you solve this problem. Now, this is an easy problem now. Why? Because it depends on two things. There are two variable things here. The g, which is a vector in the Graver basis, an improving direction, and the step size. You see, I'm at a point, like in this picture, I'm at a point, and I choose some direction from the Graver basis, and I want to choose how far to go. So the Graver basis is given. So I simply have to do it once for every element in the Graver basis. Okay, so this is given, so I just go over each one of those. For each one of those, when I plug the specific g, then this becomes this problem with the step minimization problem we mentioned before. And you can do it in polynomial time using binary search. So we can do it, and we can find the best. And the best point is going to be xk plus 1, unless there is no better point, and then we stop. And actually, we already know that once there's no better point in the Graver basis, we saw this last time, this is an optimal solution. So this is the algorithm, and of course, we assume that the set is finite. I mean, if it's infinite, we can detect this and do something. So we assume the set is finite. It is feasible because we set it to be feasible. So it's going to terminate after finitely many steps. And the question is, how can we show that we can do that it terminates in polynomial time? And then for this, we have to use this supermodularity, right? That's why I put these lemmas, so you can guess this. So, and the claim is the key property is the following. So let me continue up here. We need this vector form of the supermodularity that's here, okay? So let me continue on this board. And so here's the claim. As long as the point is not optimal, if xk is not optimal yet, suppose let x star be some optimal solution. So we fix one optimal solution once and for all, and there is one because the S is finite and the problem is feasible. And suppose xk is not yet optimal. Then the next point we are minimizing. So I'm comparing this, and then I'm claiming this is going to be something like this. Okay, so the claim is the following. The next point, you see if I compare it, this is smaller. The x star is smaller. We are minimizing. So this means that the next point, the gap to the optimal value will be strictly smaller than the gap in the present point. This is a number which is strictly smaller than 1. And it just depends on n once and for all. So we shrink. At each point, we shrink by a constant factor. And this leads to a logarithmic solution. Now, how do we show this? How do we show this? Well, so let's see. So, well, let me give you the, maybe I'm not sure I want to go through the entire proof. But how do we show this? So if you remember from last time, we're going to apply a similar trick. And the trick is going to be the following. So proof of the claim, let's say, proof of the claim. Let's look on x star minus xk, on this vector. X star minus xk. Then, well, they are both feasible. So the difference satisfies a times this is 0. This is in the lattice. And then we can use the property of the Graver basis. This is a conformal sum of Graver basis elements. Conformal sum. Each gi is in the Graver basis. And t is less than or equal to 2n minus 2. This is this integer Carathéodory number I mentioned yesterday. So we have this, and now comes the supermodularity. We plug this sum into here, and we get that fxk plus 1 minus f. Instead of x star, I'm going to now put xk plus sigma lambda I gi. And so let me see, how do I want to do this? Just a second. Fx star minus f of k. Yeah, I want to look on fx star minus f xk. We want to look on fx star minus f of xk. And this is now f of xk plus sigma lambda I gi minus f of xk. And now I apply the supermodularity lemma, so this doesn't go up. Let me continue here. So then by the supermodularity, I get this inequality here that this is greater or equal than the sum of these differences, xk plus lambda gi minus fxk. And now, so I am a little bit running here out of time, so I don't. So you do some manipulations, you do some small further manipulation, and then eventually you can conclude that so there are two-line manipulation, also some manipulations of this. We get the following thing. We get, let me try to get to the punchline here. There is some, so really this is not so, there is some I in this sum which satisfies fx k plus lambda I gi. These are lambda i's actually. Lambda I gi. Is at most t minus 1 over t fxk minus fx star. Okay, now this is 2n minus 3 over 2n minus 2. You see, if you improve the number, we'll get a better fraction here, but that's not so important. So, you see, so you do the manipulation, then it turns out there is one summoned in this sum that satisfies this. But now what our algorithm looks for the best possible improvement with some step size, non-individuals, and some element in the Weber basis. So the best one here, what? No, what? Yeah, thanks, yeah, sure. Thanks. X k plus sum lambda I gi minus fx star. You see, so one of the summands satisfies this, but we are doing in this optimization problem, we're looking for the best among all of them. So the best one is going to be at least as small as this one. So our solution, which is the fxk plus, let's call it lambda star g star from this problem over there, is at least as good as this one, and this equals fxk plus 1, because this is how we choose xk plus 1 minus fx star. So this shows the claim. This shows this claim over there. Okay. And, well, I really wasted a little bit too much time on this. So we show the claim, and then if we iterate this, so if we iterate the claim, we get that fxk minus fx star for any point in this sequence is something like this, to the k. So this is the point. So if we iterate this, this factor decrease, then after k iterations, we are that close to the optimal value. You see, we take the original one, and we get this. And now, if you choose k large enough, you can make this, let's say, a half. So if this is a half, what can we say about this? They have to be equal because they're integer valued. So here we use the fact that they're integer valued. So if I take k, and it's enough to take k something like over, you know, constant times n log f, f the optimal value, or fx0 minus log fx star, then so for something like this, we get fk minus fx star that's equal to half, but then this tells us they're the same actually, since they're integer valued. So this shows that in this many iterations we actually must come to the optimal solution, and this is polynomial time in the data and so on. This is what gives you this dependence on the f hat here, you see. The dependence on the f hat comes from this. So if you start with a value which is very, very large, it's trying to decrease. It has to depend eventually on this f hat. So this is the key lemma, really. And let me now tell you how to find the initial feasible point. Because here we set the problem to be feasible, but now we want to really find the feasible point for a given program. So, so let me go over here. What? No. I just showed you that it's polynomial. N times, this is basically, so this tells us that it's enough. It's the same that's saying you can choose it to be over n log f hat. I mean, of course, it can be large. If f hat is very large, if f has extremely large values, then it's large, but you cannot avoid this.
Right.
So, but it is polynomial in the input side.
Yeah, asymptotically, it's good. But
Where
so
polynomial time is all about asymptotics.
Okay.
So
this isn't, I was just asking if this isn't one of those cases where.
No. The constant is not bad at all here. The constant is not bad. I mean, this is the constant is that's very easy. 2 maybe or something. That's not an issue. In fact, there's a nice open problem here, but it's a little bit. So it seems that one can be able to get rid of the f hat actually of this dependency, because we really need just the order there. We're using a comparison oracle. We don't really use the values. But somehow this is a delicate issue, and we have some ideas, but we don't know yet how to get rid of this f hat. Okay, so let me tell you about the feasibility, finding a feasible point. So I'm not going to be that formal. I wanted to put this lemma formally once and for all, but so now we have the following situation. We have a set of integer points satisfying this system. Now B is given, and we are looking at this. We have no feasible point to start with, and we have the Graver basis also. So we are given the input includes L, U, B, A, and GA. And we want to do things in polynomial time in this. There's no x, and we want to see if this set is, we assume that this is finite again. We assume it's finite. You can check this. And the question, how do we find the feasible point? So here is the idea. Let me outline this. So here's the idea. To find the feasible point, or decide that there is no feasible point. So here's the idea. First, find x in Zn such that Ax equals B, or detect that there is no one. Detect that there is none. So what I'm suggesting is the following. First of all, you solve just the system of equations without the linear inequalities, without the lower and upper bound. Well, if there's no solution, then of course there's no solution here. So the problem is infeasible. If there is a solution, we're going to start with this solution. But how do we solve such a problem? So, well, I'm not going to discuss this, but actually Matthias this morning talked about lattices and finding a basis for the lattice. So basically this is it. So this is a classical problem. So this is a classical problem. Classical problem in lattice theory, lattices. And it can be solved, say by computing a Hermite normal form. Hermite normal form of the matrix A. But I'm not going to discuss it. So this is a classical problem. Do you find time equations? You have a system of linear equations. You want to find integer solution without linear inequalities. It's an easier problem than integer programming, and you can do it in polynomial time. It's basically linear algebra. Basically like Gaussian elimination. Okay, like solving usual system of linear equations over the rationals. But you have to be a little bit more careful to keep things integer and make the numbers not grow too large. No, you have the system of equation. No, that's not going to work. You have the system of equation. That's complicated. The binary search I usually just have lower and upper bounds. You have the system of equation. You have to stay in the lattice. The binary search is not going to work. So this is a hard problem. This is as hard as integer programming in general. It's not an easy problem. And in fact, we are going to actually solve it using this lemma again for an auxiliary problem. So let me explain this. So first of all, we find this solution of the system of equations only. And now we use this to set up an auxiliary problem where we can apply the first lemma. So now we do the following. So we define an auxiliary problem where we are again minimizing some function, which I'll describe in a second. Where what we do is we define the following improved, relaxed lower and upper bound So let me just give the definition and just explain the idea here. Xi, and the Fi of Xi is going to be, let me just make a picture. So F is separable convex, and this is Fi. Okay, so let me try to explain this, and then I think I got a little bit too technical in this last half hour. So let's see. So again, we start with this feasibility problem. We find one point, x, which satisfies the equations. And now we look on this, this integer program. And we do the following thing. X is this point we already found that satisfies the equations only, but not necessarily the lower and upper bounds, because otherwise we have a feasible point. And now we define a new lower bound, which is the minimum between the actual lower bound and the value of x itself. And the same for the upper bound. And in this way, we force x to be feasible in this problem, right? So by extending this, we allow the point that we just found to satisfy the bound, the relaxed bound, and so it's feasible. And also every original point is feasible. And now the objective function is the sum of these univariate functions, and you see that this is convex. And it's 0 if and only if the variable lies in the original bound. If xi exceeds, so it's either below the li or above ui, we get something positive. And so the sum of these will be 0 if and only if it's non-negative, and it's 0 if and only if x is a feasible point in our original system. And this is a separable convex function. So now we take this problem. It's feasible because this x point is made feasible. We apply this lemma. In polynomial time, we either find that the optimal objective value is strictly positive, which means there is no feasible solution in the original problem, or we get an objective function which is 0, and then any optimal solution is feasible for the original one. And then we go back to this and take the real objective function we're interested in and proceed. So this completes the whole thing. And so actually we now can write the theorem. Now here's some time to say some more. What did I want to say more about this? The main thing here. Yeah, actually not so bad, not so bad. So still we'll be able to do. So first of all, if I summarize the whole thing, then now I have a theorem. And this is now not a lemma, but there is an algorithm. Given A, its graver basis, LU, now we don't need a feasible point. And we don't need to define B in this way. We can solve in polynomial time this problem. This is the theorem. Okay, so let me state it precisely. There's an algorithm given a matrix A and its graver basis, lower and upper bounds. A separable convex function presented by a comparison oracle solve this integer programming minimization problem in polynomial time in the data and in the graver basis. So solves means that it either detects that the problem is infeasible, there's no feasible solution, or finds an optimal solution, assuming that the set is finite. If it's not finite, you can also, there's some more technicalities, but you can actually detect this and stop and say that the problem is well posed or something like that. Okay? Now, if I look on this problem, well, look here. I mean, this is really an integer programming problem, not only linear, but a broader class of integer programming problems. And integer programming problems are NP-hard. So what goes wrong here? We are given a Gravor basis. So the Gravor basis is part of the input, and yesterday I think you made some attempts to play with this, and you saw that this is really a very difficult and problematic object. And in the next lecture, we're actually going to look on a broad classes, natural classes, which are actually universal in a sense. They capture all integer programs, where we can actually compute the Gravor basis directly from the data in polynomial time and get rid of this dependence on the Gravor basis. So let me just summarize by mentioning some special cases of this, and also so here are some special cases. First of all, we can do linear optimization, linear IP, given the Gravor basis. So this is fx equals wx. This is the standard integer programming problem studied in almost all the literature on integer programming problems. It can be hard, very, very useful. I mean, in the first lecture, in the introduction, I showed you many problems that can be written down as integer programming problems. And we can do it in polynomial time. And here we don't even care about this f hat, because simply the binary encoding of the entries of w gives us the f hat in a nice way. So no f hat. So this is the usual now f hat is polynomial in the usual encoding of this vector w. So we are fine here. Then we can do norm, for example. This is a special case, norm minimization. Norm. So minimize for every p between 1 and, okay, let's say smaller than infinity. So any norm, sum of absolute values of the variables, sum of squares, and so on, we can do in polynomial time. We can also do the L infinity norm. The maximum value here. So actually this means that we can actually minimize, it's a min-max problem. You see, minimizing the L infinity norm means we actually do minimize over the points, the feasible points, the maximum over the coordinates of the absolute value. The min-max problem we can do in polynomial time. And this has application to scheduling. So scheduling, sometimes you want to minimize the maximum time it takes any machine to finish the job, so-called make span. So this corresponds to scheduling or make span. Make span, scheduling. And let me conclude by talking about arbitrary convex functions. So what if we want to do okay, let me give one more positive result. We can also do maximize functions of this form. This is something I mentioned again in the introduction, if you remember the example of the spanning trees with several linear criteria. So we can maximize such functions. Now, W is a integer D by N matrix. So each row represents a linear objective function, if you want, or criterion or utility of a player, and F mixes them together. So F now is a convex function on RD. Convex. You can do this in polynomial time also. In poly time, for fixed D, the number of rows should be fixed. For fix D. Again, the dimension is not fixed. The dimension is n. D is the number of criteria. This is fixed. And if you take D equals 1 and F the identity, you just get the linear problem again. So this is much more general than linear optimization. Okay, and finally, let me mention a hardness result. So here is the last thing for this talk. Can we minimize arbitrary, not separable, convex F? What do you think about it? Well, I said the hardness problem, but so we are minimizing special convex functions. Separable convex functions, they're not very, they're very useful because they include all the norms. And you've seen in the feasibility, actually, that I use strongly the fact that I can minimize separable convex functions, sum of piecewise linear functions, and so on. But can we hope to minimize arbitrary convex functions if we have the Graver basis? Well, the answer is no. So no. And here is a simple reduction. Consider again the subset sum problem which I mentioned before. So we are given numbers. Let me write it in scalar form. We are given positive integers. And the question is there a partial sum that some of these numbers, is there an I such that the sum of the numbers in I is A0. And this is known to be NP-complete. This is a classical problem. Okay, is this clear? We are given n plus 1 positive integers, and the question is there a subset of the numbers from 1 to n that sum to A0? And this is NP-complete to the side. And so we can easily encode it in a simple convex, non-separable convex problem, which we cannot solve even if we have the Graver basis. So let me conclude by showing this. So, well, this problem is equivalent to minimizing okay, so let's see, I'm saying this is equivalent to this. Why? This is the zero matrix, let's say, of one row of zeros. So look on these points. Which are the feasible points? They have to be integer. This is not a restriction. Every x satisfies this trivial equation. And they have to be integer in between 0 and 1, so they have to be 0, 1. Whenever you take a 0, 1 vector, just encode the subset sum. This square is always non-negative, and it's going to be 0. So the optimal value is going to be 0 if and only if there is a 0, 1 vector which gives you 0, which gives equality, right? Now, so you see this is a convex function. It's not separable convex, but it's still a very special and simple convex function. It has rank 1, for example. If you write down in a matrix form, then V has rank 1. So it's a simple, fairly simple convex function, and we cannot hope to minimize it in polynomial time. But what is missing here? I mean, to minimize in polynomial time, we need something. What? The Graver basis. So how about the Graver? Can we compute the Graver basis here? What is it? It's not empty set. The empty set was if the columns are.
Too many. It's too big.
No, it's not too big. No. If it's too big, then this would not be NP. What? Yeah, the unit vectors. So again, the Graver basis is empty if the matrix has linearly independent columns. In this case, the Graver basis is simply of this matrix. No matter how many rows of zeros you have, is exactly the set of all plus minus unit vectors. So it's not big. It just has two n vectors, and so you can actually immediately compute it in polynomial time from the data. Just write it down. So here you have the Graver basis, and well, you cannot optimize in polynomial time. So separable convex is but I should say that, let me mention, we can optimize in polynomial time some non-separable convex functions using these techniques. And this is a recent paper that I think it's mentioned in the book at least. It's a recent paper of, well, recent paper, I mean. Recent paper on Graver cone. So we actually were trying to see how far we can go. You see, you cannot get any convex function, but still there's a nice class of convex non-separable functions which are either quadratic or polynomials of fixed degree, where you can actually extend these techniques and optimize. Okay, so I'll stop here. Next time I hope we'll start chapter 4. So, any questions? A bit technical. No, that's fine. Okay, so see you after lunch.